Hello to viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about Microsoft Project Silica. So let's dive deep into it. Now, what exactly is the problem that we need Project Silica to save us? Well, the problem is that we are making stupid amount of data. What does that stupid mean? Stupid means it has so many zeros, it exceeds human comprehension. Meaning I can tell you those numbers, but it will not make any sense. It's like listening to $5 trillion. It's like it does not make any sense. Like the too many zeros, like you do not have a actual context for it. So we have reached that point where we are making bonkersly large amount of data and we cross that stupid threshold, meaning it's just like, it's too big, like the numbers are too big. And there is no actual way of archiving it. Let that is very clear. Data storage and data archiving, they are two different puppies. Archiving is I put it, I forget about it. I'm done. Me sorted. Me go. Me done. Put and forget. That's the aim. Now, like back in the days, you printed copies, you put it in library, you put and forget about it. It's like that data would be there decades from now. And again, same with film. Back in days, like you will have the film that is going in the machines and print, and then you'll have master print that is archived on like a high grade, a long lasting film reel. And then once you have tested it, that is good, everything is fine, then you put it in a container and put it in archives. You never ever think about it. It's there. It's gonna be there for a very long time. So that's what we call archiving, meaning you do not have to think about it. But when it comes to our data, there is no technology. We came very close once, but we do not have actual option. So right now what you have is hard drive. Most poor people and low cost people deal with this. What is this? This is basically a mechanical drive where you have platter has magnetic systems, magnetic domain that you can flip. Okay, that's cool. It works. Awesome. GG. Here's deal. It does not last. By design, companies will not trust this puppy more than 5 to 6 years. 8 years is like pushing it. 10 years, it's gonna break. Now, here's deal. If you're running it, it will die much sooner. And if you're like, what if in 2020, I put data on it and put the hard drive somewhere? Right? Let's say a very weather controlled dry environment. You put it there, you forget about it. What happens after, let's say, 10 years? Would the hard drive work? Maybe, but let's say it work does not guarantee that data in it would be intact. It will go through what we classify as data rot, meaning multiple of the bits would have been flipped. Even if this could do error correction, it will be like, hey, I have too much damage to recover from it. That's why this is not what we call archive grade storage. This is active storage. You're putting data in, you're checking the data, you're recovering the data, you're dumping energy into it. And again, you want a lot of data about it, like how real this real is, like, enterprise data. Look into Backblaze. Backblaze produces a lot of data on real hard drive in real industrial scenario. It's like, how long do they last? Most of them never touch 10 years. They're like, I have 15-year-old hard drive, good luck. Most people don't. And again, do not trust your data on it. Data will go through rot. So that's a very low grade solution. We rely on it, but it's not a long-term solution. Then you may think, what about SSDs? Basically NAND flash. Now, flash is basically what is happening there. There is a physical wear component, but question is, if there is no moving element, how the heck you have wear and tear on SSDs? Wear leveling and all that. Why do you need that if there is no moving components? Well, what wears is this puppy, meaning you have the ability to pump electron into it, trap electron in that floating gate, and dump it out when you want to read. Okay, cool, awesome. You can push it in, pull it out. But here's the deal. That fundamentally means you are changing the state of that place from equilibrium to unequilibrium, meaning it's like heating it up. Basically, if you heat anything up, let's say a glass of water, it will try to reach to a point of equilibrium. That's the law of universe. So electrons that are trapped in the quote-unquote gate, floating gate, it will leak out. Now, of course, it will not happen day one. It will happen very slowly, 5 years, 15 years, 20 years. But sooner or later, it will reach a point where enough of those electrons would have leaked out that even though SSD could be working, it's like it's completely fine. Heck, it would be better than this because there is no wear and tear. It could easily be like, hey, yeah, all the data you put inside me, yeah, that data is lost. Data has rotted away. I have dealt with it, and many of you may have already dealt with it if you are not double checking everything again. So fundamentally, this does not last. That's why no corporation, companies, enterprise will ever trust their data, archive data on these, nor this. So what do? Well, we have no actual solution. So the next best thing is put everything on VHS tapes. Now, I know it's not VHS tape, but you get the point. Like, that's how difficult it is. And these tapes are basically, they're also not reliable. They can only last for 10 years. And most companies do not even let it to go that point. Because again, if you have 3 tapes, all of them written in the same year, and you waited 10 years, there is a tiny probability all 3 could be corrupted. So they generally, every 5 years, they cycle the data, check everything, apply checksum and all that. Basically, it's an active medium. It's much slower grade active medium, but it is still an active medium. You have to treat it with care, and you also have to upcycle it, meaning you will start with LTO5, let's say, and then you're like, okay, now I have a lot more data. So now you dump all the data again into LTO6 tips. Now you're gonna wait few years, again LTO7 tips, wait few years, LTO8 tips. Right now we are at LTO8 or LTO9. So we are reaching a point where it's hot potato game with dumping data from A to B, A to B, A to B, A to B. We are not put it, forget it. Like how back in the old days of movies, where it's like you had the movie, you put it in a container, seal that container, and you forget about it. Like you're like, bro, we done. We done. We do not have to do anything more. That is not possible. So we are just reaching hot potato with our media. So, and be mindful, every time you're copying data from A to B, there is a probability of checksum error. There is a probability of data rot. It does happen. And yes, people have lost it even with enterprise grade equipments. It happens. So fundamentally, we do not have any scenario where we can just put the data and forget about it. So it's very expensive and maintenance heavy. So that's a very big ass problem given how important the data is to our life. So what is this Silica? Now Silica is 5D data storage. Now it's nothing fancy, it's just instead of 2D, it's 5D. So 5D data voxels are made on subsurface laser engraving. So you take a glass box, you must have seen like in malls and all that, where you have glass box like a cube or a sphere, and inside it is there nothing on the surface, inside it, bubblogram I think that's called. So similar technology where you have a laser engraving things inside the block, not on the surface, inside the block. And you are doing that. Now on what you are doing it? You are doing it on quartz glass or silica or SiO2. Now key part is this is quartz glass. Normal glass is soda lime glass. Generally it's a quote unquote contaminated glass where you are using soda and all that to basically make it more malleable, more easy to deal with. So it melts very easily. You can make, it's more than good enough for our day-to-day use. And if you try to deal with this, the furnace cost alone will bankrupt you. So what happens if you do that? Like what if you actually deal with SiO2, high purity, high crystallinity, and like what is the benefit of that? Well, you get chemically inert puppy, meaning heck, normal glass is almost chemically inert, meaning you have to have very specific thing that can even attack it, let alone destroy it. And this puppy is like even higher level than that. It's again not as good as platinum, but it's very close, meaning oh, what happens, a tsunami happened, like all the garbage water happened, nothing. What happens if sewage water touches? Nothing. What happens corrosive gas goes there? Nothing. It's like there is very little things that can do something to it. So that's chemically inert, meaning you put it, you forget it. It's not magnetic. And then it's thermally safe, meaning compared to all the plastic system, most of them go bye-bye the moment we cross 200 degrees Celsius. I'm also giving too much headroom, 200 degrees Celsius, but you get the point. They are not thermally safe. These puppy, because again, pure crystallinity, 1000 degrees Celsius is like, bro, I don't even care. So meaning you can literally have this server literally working in Africa or in India, and it's like, bro, I don't care. 65 degrees Celsius air temperature is like, I do not give a damn. Thermally safe till 1000 degrees Celsius. What does that mean? That simply means you cannot oops it. Like, oops, somebody threw a cigarette, it catches on fire. Yeah, that's not happening. And yes, catching on fire was a big issue with all the films. A lot of them catch on fire. So here it's thermally safe. It's like, I got this, fam. Me good, I got this. And it's very robust. So because of the pure structure of it, it's not like I dropped it, it will fall, nothing. Like you have to work hard at it in order to crack it. Like you have to actually work hard at it. Like I'm trying to break it. Like you have to use a bulldozer or something like that. So it's not like oops. There is no oops probability with this. Scratch resistant, again, you go with a diamond picker, like of course it will break. But it's not like oops. Another aspect is resistant to radiation. Now be mindful, there are 3 puppy radiation which we call alpha, beta, gamma, and then there is a daddy radiation which we call neutron. Nothing in this universe can withstand neutron radiation. So do not even attempt that. It's just that if you have very little of it, it's not going to be a very big deal. And alpha, beta, gamma, because alpha and beta are charged particle, if they go through your electronic media, especially flash gates and magnetic strips, yeah, bye-bye. Yes, that's why those things are not supposed to go through X-ray. If you send them, good luck. And yes, more than enough people have lost their data going through X-ray machines. We have learned it the hard way. So that's why resistant radiation, meaning unless you have something very ludicrously high radiation environment, these things are like, bro, I got this. I do not care. Like you can store everything in Chernobyl. I don't care. So what about the laser that is etching it? That laser is generally from 800 nanometers to 1000 nanometers, and it's ultra fast femtosecond laser. What does that mean? That simply means you take a few kilowatts of laser. That's not that great. It's like, okay. And again, you are talking about something that can withstand 1000 degrees Celsius. So how the heck you etch it? Well, you do not. You take that 1 kilowatt of energy and you just compress that puppy. You compress it. Now, how much you compress it? Under 100 femtosecond. It's stupid number. It has too many zeros to make sense. So if you've done that, it becomes ludicrously high. Let's just put it that way. And that is so precise, so controlled. The polarization of the light affects how it melts glass inside. So changing the polarization, you can literally change the angle of the line that is causing. So that's how we do that. So x, y, z, that's a normal coordinate system. X, y, z, normal, 3 dimensions of spatial coordinate. The brightness, basically how powerful that intensity was of the laser, that's one coordinate of the data. Like in DVDs, you basically had a light going dim, going bright. Basically constructive and destructive interference was there. So all it was changing is one dimension where it was living high, low, high, low. That was one dimension data. That's same in your hard drive also. It's one dimension. Here it's like high, low, high, low. Okay, cool. But here it also has polarization. And be mindful, these things, they are not single dimension. They are not on or off. In polarization, it has, if I'm not mistaken, 4 to 5 states. There's like tuk, 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 tuk. So a lot of binary data can be there. And brightness also is not like full brightness or minimum brightness. It's like, I think it's 4 to 5 states. So multiply 4 multiplied by 4 in each voxel, that's a lot of data. So each of the thing that you are seeing, that's how the data is being read. It's bonkersly large amount of data in a very small unit, and that's why the density is so high. CD and DVD, they always had like, a light going brightness. Imagine that it had like, oh, red means this bit, blue means this bit, and then it had brightness also. So two of them can independently hold 2 different data streams. The physical space of that data would be compressed beyond belief. That's why it has so high density. Like the amount of data you can pack into this, they stopped figuring it out. Like they literally gave up on that. They're like, dude, we reached a point where it is good enough to like LTO 9 tapes. We are not gonna push further than that. Not because they cannot push it, but they're like, other things are the bigger problem right now. Though basically how quickly you can write it, how quickly you can verify, those things are the weak link. They're sorted in terms of density. They're sorted because of these 2 vectors. And be mindful, these 2 are working on one vector, voxel. So where the voxel is in 3 dimensions, that can also be a data point. That could also be helped in their error correction. So the amount of density, the oomph, it's bonkersly high. Nothing even comes close to this. And given the fact that it's like, I do not care, like you do not have the ability to destroy this easily. Like you have to put effort into it. Like you have to actually throw them into a metal furnace like a T2 Terminator. Nothing else is going to bother with. And it's a write once, read many. It's a worm media. We want a worm media, meaning you want your backup to be like, oh, somebody attacked a ransomware in my computer. It's like, you want this puppet like, I got this, fam. All data flush, new data done. Again, somebody attacked the virus. It's like, I do not care. You cannot rewrite me. The end. We were so close with that with M discs and DVDs and Blu-rays. So Silica is like that. That's what we want. Like once you put the data, it cannot be corrupted. Once you put it, you verify it, you're sorted, you put and you forget. So how exactly we read and write? Now, it's a very intensive process. We are talking about femtosecond laser. It's an intensive puppy. And it does require 2 layers, X and Y, and there are hundreds of layer on top. Yes, so layer by layer, it can go up to 100 to 200 layers. Like if you know from DVDs, we went from single layer DVD to dual layer DVD. People are like, whoa. Then we went from Blu-ray, dual layer Blu-ray to quad layer Blu-ray. I've only seen one company that releases Sony BLXQC, that is like 128 gigabyte, one disc. I have the writer for it. I just don't, it's not sold in India. The highest disk capacity I have is 100 gigabyte. So imagine that same technology where you have multiple layer. Now imagine that layer to be 200 of them. So let's be very clear. The density, data density, I can easily see this. Once this technology becomes more mature, more actually in use, I could easily see that in future. They're like, yeah, we have 10 times the density because none of the physical variables are maxed out. They're like, we sorted, that's done. That's more than a scope is there. We are figuring out how to read and write fast enough. So that 2D dimension they have to know, and hundreds of layer. Okay, now how the heck you are actually doing it? What you are doing is basically you move the stage, quote unquote, and you see the laser. Now this is why your CD spins. So because there is a track, there is a spiral groove. That's why I say CD is actually just one dimension. It's just one long string of data. Here they thought of that, but the reality was if you're spinning it, it's very cumbersome, very expensive technology. It's like, what if the laser spins. So like, how can we do that? Well, in future we will do that with phase shift array. It can be done, but I've not seen somebody trying to do that. So right now we have a galvanometers. So two mirror like going super easy. Heck, your barcode scanner does that. It's super cheap nowadays. So that's what we have, X and Y. And every time that voxels that you're seeing, the color changes that you're seeing, that's the intensity. And the lines, here it will be easier. Yeah, the lines, they have lines, that's the polarity. So each voxels have two data points, what is their intensity and what is their orientation. Both of data creates a bigger palette. That palette is a block. That block has a lot of data. And then you have hundreds and millions of them everywhere. And I do not know, like they never specify what is the size of that each block. And now benefit is how the heck you're going to read it. femtosecond laser, writing it, cool and all. How the heck you're going to read it? Well, they created a different technology. The technology is very ancient technology of polarized sensitive microscopy. It's nothing fancy. It's just a microscope with white light, not laser light, white light. You can use ultraviolet lasers on it if you want, but it's unless you have femtosecond laser, you cannot destroy it by reading it. And normal light, normal microscope with a polarizer, you're more than good enough. So basically you take snapshots of each axis, basically each layer, and each layer you are reading at one time, and based on you take one photo, change the polarizer, take another photo, basically you do this 4 times, and then move to second layer, do this 4 times, move to third layer, and now you have a 3D data cube, so to say, and that has boatload of data with error correction and all that jazz. Now be mindful, because of the bonkersly high data density that we are talking about, this puppy is unreadable. That's the only part of this technology that is like, eesh, it's unreadable without machine learning. Meaning it's not an algorithm, you cannot make a ASIC to it. You need a freaking neural network processor for that. It's a very complex, like the amount of complexity, and they're developing the algorithm. And I think this may be the second reason why they stopped at the data density, where it's like, bro, we can make it far more dense. It's just like reading it will require a supercomputer. So I think that's why right now the data density is like, So, but it does require, let that be very clear. Writing is not that complex. Reading it reliably without even a single error, yeah, that's difficult. Again, it's not impossible, it's just that it requires extra layer so you can pass the signals. Basically, signal to noise ratio is not that great of this whole system. So it does require some machine learning to filter things out. Now, what about the library? Because again, every nation has what we call national archive, be it India, be it America, be it whatever. So how do we store a country? While the plate could be very dense, you're going to need a boatload of plates. So this is the idea. Now, LTO tapes was using basically same technology invented in 1950s, where you have like, shelves and you have things moving around. But here's the things moving around is almost in one dimension. You can only move this way, only move that way, but you cannot crisscross it. So Silica library was designed with scale in mind. Basically, it's what I always say, Mark 1 is always garbage, Mark 2 is better. So Mark 1 was LTO tapes. They're like, okay, what is broken in this system? How can we improve it? So they went to this puppy. Now readers and writers are load based. Thankfully, because of these two systems, they can design in such a way where if data temperature is high, meaning everybody is requesting reads out of it, they will be like, okay, we're going to put a lot of readers. Readers are low cost device, so it does not require to be very expensive. They can put it. But if it's a very low temperature data, basically people are dumping data once in a while when they get ransomware attacked or some maintenance downtime or some weird event, then they require it. So then you will have like, very few reader. And what about data ingest? But again, if it's a backup company, they're getting ingest every day. So writers, they will put far more writers. Because of these two things being separate, you can reduce your what you call idle load. Meaning you're like, do I actually need, like, because whenever you are buying LTO tapes, every player is reader and writer. Now again, from ease of use point of view, it's very easy, but consequence is it's a very wasteful, so to say. And corporations do not like to waste. Well, they do not give a damn about the machine, but they do give a damn if the machine is not doing anything. So that's the idea. So you're gonna scale it, and I can easily see in the future where they have like containers where it's like, oh, they need one, like, massive data surge is happening. They can just keep sending container ships there where they're like, writers are in the containers and like writing it exponentially, and then they move that same unit to other warehouse that requires it. So having these two vectors independent, basically femtosecond laser writers and microscopy readers, they could be completely separate. You can have like 50 readers and only 2 writers, and you could have opposite where like 500 writers are there, barely 15 readers are there. You can do that, and be mindful, it does have the benefit because it's a 2D access. You can find exactly where your data is on that single plate. You no longer have to spool the whole goddamn LTO tape. So that's there. And racks are passive and caseless, meaning this again, they also learned from the LTO tips is like once you have the case, it becomes an extra point of failure. So what if you don't have it? And be mindful, magnetic tapes require case. It's not like bad design, it needs it. This puppy is like, I don't get this. Like it does not have to care. Everything that is complex, it's only in the robots. Now this robot is called Rascal. Do not ask me why it's called Rascal. It's called Rascal. Microsoft named it. Somebody was having fun with it. So idea is all the complexity, all the mechanism, the gears and stuff and hulululu, that's in the motors and drivers and all that. So person is going to go there, put it there, and it's going to keep moving and collect it. Now, can this read it? As of now, it does not even have the retrieval mechanism. This was just a proof of concept. So in future, I could see it. Microscope is not that big of equipment, and I could see in a future where they'll just like, hey, the robot can read it directly on situ. How would it transmit that much data? Maybe millimeter wave. That's the only thing that is dense enough to transmit data. Could be done. Or right now, the current hypothesis is that you're gonna collect it, put it in a writer machine, put it in a reader machine. So this right now is just a hand that moves things around. Again, we have the same thing with LTO tape libraries. This is just much more upgraded version. So racks are passive, caseless silica disks. Rascal is gonna go and collect it. And if Rascal breaks, which again, it will happen, is a mechanical component with moving parts, you're gonna replace the robot rather than the whole stack. So super is there. And you can have multiple Rascals in one row and column. That's what the design part of it. It comes there. The second one is blocking. It's like, okay, I'm going to yeet above you, put it back, be good. Videos down below. So that's the idea. And again, if you're talking about a nation, every year you're going to make bonkers amount of data. Keep stacking it. And be mindful, the stacking is on 2 axes. Not only you can make it longer, you can also make it taller, because these things can actually hop from bottom to top. So it does not require a mechanism to travel on top. It's like, I got this. It can literally hop. So, and if you make it very large array, you can have multiple robots in each array. So read and write and collection, verification, all that could be very fast. So the library part is surprisingly well sorted. And I'm genuinely waiting for somebody to like, what if we put this in LTO systems? So, but I don't think this like worth changing that much, but this is genuinely well thought out. Like somebody actually sat down and thought through this. It's like very well designed. Now, what is the hope? Well, this is the first time in principle that we can reach a point of very long-term data storage. Now, would this puppy last forever in space? Yeah, most likely. Even on Earth, it should last for thousands of years, because again, it's inherently in Earth. There is no magnetic field to change, and all the alloys, because it requires femto freaking second laser to change it. It's not that likely where it's like, oops. Now, of course, there is a half-life element of silicon and oxygen. So there is a point where it will like, bruh. But that's very far, bruh, right? That's not right now. That's like farther, like you have to travel further than Egypt, further than pyramids to even bother with this. Like it's sorted in principle. So it's basically we are reaching what we always needed, put and forget, meaning you put your school memories in there and you forget it. And then in your deathbed, you can actually look at it and it still have full HD videos. So that's there. Now, this solves the cloud storage right now, meaning it solves the cloud storage problem where they actually hope that nobody keeps buying the more and more storage, because where would they store it? Because many times we are like, oh, cloud. Cloud is someone's computer that you are renting. If the computer technology does not improve, we are stuck. So that's why I can now finally see a scenario where long-term archive, they're like, we good this. Because be mindful, by law, they require it. Like banks require a serious amount of data archiving, like serious amount of it. And they will have like lot of writers, barely 1 or 2 readers. So now I can actually have some faith in our digital world that the current rate of growth is like, I got this in principle. However, I have a doubt that it will ever come to the masses, because I do not see this technology even being built or approached as like, what if people want to back up their data? And there is no incentive there, because we no longer have physical media, which again, I do regret. The problem is that if common people do not have access to this sort of archiving technology, our history is in their hands. Now, who is they? Well, they could be anybody. Like imagine this, well, let's say you are a country, some invasion happens. Again, it's happening right now. So, and all the data was in those archives, they just destroyed it, the end. Like the only reason history is not erased that easily after printing press is because clones of data was created, multiple clone of them. And again, if this sort of technology was available to person, now you decide what is important to you, just keep it. And if Google decides or goes bankrupt, realistically, that could happen. It can go bankrupt, bought by some other company. Your data won't be like, bye-bye. Even though data is physically there, they're like, bye-bye. or it could not be even held against you as a ransomware. It's like, hey, pay the data or I delete your data. Because okay, deleting the data would be just like, I'm going to put it again, remelt the glass, recycle it. So that lack of data, basically it puts us back into that era where, because of our reliance on digital data, if libraries are burned, we are lost. Meaning a country could get invaded and their 1 or 2 generation goes by. If that time they deleted the data, we won't have anything. And be mindful, cassette tapes played a role in revolution. VHS tape played in roles of a lot of data transmission, underground networks and all that. And again, we could do that with CDs and DVD, but the ease why people are giving up all the control and reliability of their own data storage is scary in long term. Not in 5 years from now, but in 50 years from now, that's a very long term storage. That's a very serious thing. So I'm very hopeful. I'm happy with this technology, but lack of that, even a talk, like what if people can have access to this? What if people decided what is important? Like they buy one plate, they go to a library, etch, like, every month, let's say once a month, they etch whatever the data they have. Because again, one plate can easily store a person's life. So, and again, they could claim, have 2 or 3 if they are rich enough. So not having any person's access, only having corporations access, again, data is important for all of us. And as our data rate grows, we do not have any physical media to store it. The last thing I can recommend is just the M disk. And be mindful, DVDs, while they solved one of the CD's biggest weakness, the data layer being on top, they did not solve the dye. The dye that was used to make that layer, it's vulnerable to moisture. So if you have DVDs, moisture gets into it, it destroys it. So M disk is designed to solve that, but again, we do not have enough of it. And again, the capacity is not that great. It's like the highest of verbatim disk is only 90 gigabytes. So lack of physical media is dangerous, like in long term. Like I studied history and then like, yeah, we need it. You want almost every Tom, Dick and Harry to have a time capsule, at least for them, for like, 5 years from now, 50 years from now, 500 years from now. Like we used to do that. We have negatives of that era. We don't have from now. And this is the first media consumption where somebody actually paid for it. Like Microsoft Azure, Superman, the movie, the first Superman movie was now etched into this thing. Like that's what they are showing, like the tapes and all that. And you were like, isn't tape better? Yeah, no. Tapes have fundamental limit. One mild fire done. Another aspect is they self-degrade. The inks, the dyes, silver halides and all that, just they degrade. They are not like, I put it, I forget it, like how, Christopher Nolan talks about it. Bro, these things self-degrade. We have lost so many movies because they self-degraded. They were sealed. They were put in a salt cavern. So no water, no moisture touched it. It's just like, that's why I said, like, I'm very happy that this technology happened. I just wish something like that touch a human person. Like not corporation, human. So this was my presentation on 5D data storage and Project Silica. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.